Okay, good morning. So, first thing before I forget, there's some post on Piazza about people wanting to extend homework 8. I just want to make sure that everyone's okay with that. We have no problem extending it. It's a trade-off between, you having one more day to do these 3 problems or to turn them in, and also seeing the solutions. They'll help you prepare better for the midterm. So if you're okay, if we make it like Saturday midnight instead of Friday, then you have Sunday to review. Is that better? Raise your hand if it's better. Okay. By a law of large numbers, I'll extrapolate this to the whole class. So, okay, we'll make that then basic. We'll post the solutions hopefully early on Sunday, so before you wake up. So you can take a look at those. There's a post about what's in scope. Basically, what we do today will be the last kind of set of things content-wise. I don't want to, there's a whole list, so read it on Piazza, but basically capacitors, capacitive charge sharing, that type of stuff is in scope. What we do on Thursday, which we're going to start the op-amps and things like that, that's not in scope. All right, so it's just what we've done up until and after this lecture and associated discussions, right? And homework 8. Okay, so what we were looking at so far is we started building this capacitive touch screen. So that's our primary objective. And now we're going to go and draw a real geometry of that capacitive touch screen and apply what we did last time in terms of looking at where are all these capacitances, what is actually the sensing capacitance, and then figure out how to design a circuit that will actually measure that capacitance. Just like we did with the resistive touch screen, we figured out that the dimension is a function of resistance, and then we devise a circuit to measure that resistance, right? Or turn it into voltage. So let me draw a little sketch here of So what I'm drawing here is essentially the top view of your touch screen as well as the side view. So let me just be a little bit more precise. So this will be our electrode E1. This will be our electrode E2. They're sitting one on top of each other, right? So electrode E1 is, I'll draw a side view. So this is E1, and then there's E2. And then there's basically, there's the surface, right? So just to put my finger, I would put it basically here on the top surface of this. So this is glass. This is top surface. Right? Electrodes E1 and E2 are just pieces of metal, right? Metal wires that sit, or little metal sheets, right? And so if you take a look at this section over here, that's essentially this overlap area between electrode 1 and electrode 2, right? So I can expect to have some capacitance here. Right. In reality, people who have kind of done some physics will know that each part of the conductor actually terminates the field, right? It's not just the bottom plate. So in reality, even this side would actually have some that's called fringe capacitance to this metal, right? So it would go something like this, right? Because if I draw the field lines, electric field lines that go out of this, if I was to put charge, the electric field lines would be going like this, right? even a little bit from here. Right? That's how the lines would go. So wherever the field lines go, there is basically an effective plate. Right? But for all intents and purposes here, we're just going to assume the wire is wide enough that really the bottom plate dominates. Right? So it's this. So we can say that C E1, E2, and we're going to call this, let me just write it better. So we'll say C E1, comma E2. That's basically this capacitor. No touch. Equals some epsilon times A over D, where A is going to be approximately this area, some effective area of overlap of these two conductors, and D is basically this distance. So there's nothing new here. Just two parallel plates. We have the capacitance. Right. The fun begins when I put my finger on it. Yes?
Does the area refer to the area between the two E1 and E2, or the area between?
The area. So this is the top view. Top view. And this is side view. Right. So the capacitor is between the plates, and the plates in this picture, you see them like this, right? So the area is actually visible when you look from the top, right? It's the overlap of these two wires. So that's this area, A. Does that make sense? Okay. Any questions about this? So far, people get it? Okay. So let's draw a case when we put a finger. Right. Two. Okay, it's my artistic rendering of finger. So now when you put finger, we said that the skin is conductive, right? So basically, and the whole like everything on the finger, so even these. But like again, just like with this guy and this guy over here, we're gonna mostly look at basically the bottom plate. So it's essentially how this plate, if there was charge here, how that charge, the field of that charge terminates on this wire and that wire. Right. So effectively, what you have here is this capacitance that we already had. That was CE1, E2, no touch. But you also have some capacitance that forms between the finger and this electrode, and also between the finger and this electrode. Because from that standpoint, this is one plate, this is another plate. There's still some field that bypasses E1 and terminates down in E2. Right. So we're going to label the finger as node F. It's just like a node in the circuit. This is E1, E2, this is E1. Then we're going to label these capacitances. So this is CE1, E2, no touch. This is CF E1. This will be CF E2. Okay? Still, all of this around it is basically glass. Right? So, we're going to draw an equivalent circuit of this because I don't want to carry this physical picture with me all the time when I analyze the circuit itself, right? So what we have here is we have node F, right? That's this node. And then we have CFE1. Then we have node E1. Then we have capacitor E1, E2, no touch. And from this finger, we have another capacitor, which is CFE2. And then this node is E2. Does this make sense? Yes. What? So maybe we should just relabel it. So the capacitance between E1 and E2 is this one. I just labeled it CE1, E2, no touch. What's your favorite label? Let's do it. Let's say, should we just call it, I don't know, CE1, E2, N? It's just a value, right? So CE1, E2, N, right? So. Right? So it's just a value. It's the value of the capacitance between just nodes E1 and E2 where the finger is not present. When the finger is present, you get these extra two capacitors. Okay? And now the question is to figure out how has the capacitance changed. Right? This setup is really cute because I only will put my measurement circuit between E1 and E2. I don't have to worry whether the finger is grounded or not or anything. Right? So my circuit will look what happens between these two nodes, E1 and E2. Notice that the finger node is just between these two capacitors. Okay? So I want to redraw this circuit so that I can more easily see what is the equivalent capacitance between nodes E1 and E2. Okay. So let's do that. So what I'm interested in is having, let's say, E1 here and E2 here as a terminal, and then seeing what's the equivalent capacitance in between. So the first one we see over there is between E1 and E2, we have our old CE1, E2 no touch, right? So that one, we'll draw it. That's the one over here. Right. Okay. So can anyone tell me what do we have on this other branch? So I'm going from node E1 up to F and then down to E2. What kind of setup do we have in this branch, this other branch between? Take a look at that plot. Like from node E1 to E2, how many paths are there? There are two paths, right? One straight down and one around, right? So yeah, you had it.
Isn't it just a series of CFE1 and CFE2?
Yes, yes. So it's basically CFE1 and then in series with CFE2. And what's this node in the middle? That's the finger, right? Okay. So you see, from the standpoint of the circuit that's going to do some measurement here, I don't care. I just care that the finger is there because it creates these two new capacitors. But like, I don't really care about what's the potential on that node necessarily, right? So that's why all this stuff that we talked about, whether the finger is grounded or not, zero potential, that doesn't matter at all, right? I don't care what's the potential of the finger. I just care that it introduced these two capacitors that I can measure, because I'm going to be measuring total capacitance, right? Okay, so what I really want is to calculate what is C equivalent, or we're going to call it C E1 E2 touch, right? So this is electrode E1, this is E2. So why don't you take like a minute, talk to your neighbors, and figure out what's the equivalent capacitor there. Do you know? Do you know?
So are you going to be there for officer?
Okay. Any ideas? What is this equal to? Let's say topologically, before we kind of spit out the formula. These two we already heard are in series, right? And then, does anyone want to? Yeah. Yeah, it's not going to be equal. It doesn't have to be equal. Yeah, just topologically, these two are in series, and this one is what? In parallel with this, right? So, okay. How do we start? Yes? You mean parallel operator? Okay. So, let me start from the, maybe the other side is easier, right? This one is in parallel with something here, right? Therefore, what is going to be the total equivalent capacitance? This plus whatever is here, right? Okay, so here we have CE1, let's write it here, equals CE1 E2 no touch, plus, this plus comes from basically this CE1 E2N being in parallel with some equivalent capacitor here. And then we look at what's here. It's a series of two capacitors, which unfortunately is mathematically, we show it as a parallel operator, right? So it's then CF E1, parallel operator CF E2. If you're confused, that just evaluates to CE1 E2N plus CF E1 times CF E2 over the sum. Notice that this is strictly larger than just this piece, right? We're going to call this touch, right? So this piece over here is our delta C. That's what we're looking for. Right? When you bring the finger close, that's the extra cap that gets created, and we're trying to measure that to see how much the original capacitance changed when the finger got there. Right? Okay. So now, as in any design, we need to kind of have a specification what we want it to do. So we said early on that our overall goal is to have some change in capacitance. We have some C measuring circuit. And that will produce some change in voltage or change in current, right? And then we'll be able to know something happened, right? There was a finger there or there was no finger. Right? So now let's think a little bit, how can we create this measurement circuit? Right? So there's basically only one formula that we learned that will help you kind of do that. And that's Q equals C times V. Right? It's kind of like an Ohm's law equivalent, but for capacitors. Right? So that means if I have a capacitor, C, and I have charge Q on this plate, so let's say plus Q here, minus Q here, the voltage between these plates is V. Just like in Ohm's law, it's important to see where the signs are. Like passive convention, in Ohm's law, we had something like this. It was an R, there was a current I, and then a voltage V. And voltage V was I times R. But only in this condition, where the current flows into the plus kind of orientation of the voltage. Same here. And you'll see this is actually key. If you forget this in capacitors, you're not going to be able to do any design. But if you remember it, it will be very easy. So just like these are basically the two conventions that will solve all the circuits that you've done so far very easily. So just remember them. So with this, we can explode a little bit what's inside this circuit. If I get delta C in, the first thing I'm going to do is try to turn a change in capacitance into a change in charge. Okay. If I want to do that, what does voltage have to be on that capacitor? So I want C changes, I want Q to change. What does V have to be? Constant, right? Because if V changes, then I don't know which changed. Did C change or V change, right? So the first block was going to be basically turn, we're going to call it delta C to delta Q at V fixed, right? Or V equals constant. V okay, so the equation will be something like delta Q equals delta C times V fixed. Something like that. Right. Then what we get here is basically delta Q. So how much extra charge we got. And now here, we want to turn the charge into voltage. Right? So again, if I look at this, in this other block, I have charge that has changed, and I want to see a change in voltage. So what should the capacitor be? Constant, right? So this is some other capacitor, right, that I'll be using. So at C fixed. So that will be something like delta Q equals C fixed times delta V. Okay. I can then just go and replace delta CV fixed in here and essentially find that, we have maybe right here. So we have delta CV fixed equals C fixed delta V. And from here, delta V is delta C over C fixed times V fixed. Yeah. Okay, I don't know if it's going to be better. Is it too yellow? Faint? I can press harder. Okay, let's see. Okay.
Your right finger too, please.
Yes. Okay. Is this better?
Yes.
Okay. So from here, we have that delta V is delta C over C fixed times V fixed. So notice we're not really rigorously right now solving the circuit. This is just kind of intuition, right? See how these variables kind of relate to another. We're going to go and solve it in gory detail. But just it helps to kind of do these things on the back of the envelope to see roughly what value, what quantity can convert to what other quantity. And then you go and break it up. Right? But we see here that we can indeed get delta V to be proportional somehow to delta C. Right? And that's what we're going to aim to create. Okay. So to do this type of thing, we're going to label this whole node, we're going to call it basically CS. So this will be the sensor capacitance. Like when we touch, we will measure that value. And the sensor capacitance, sorry, let's do it like this. So sensor capacitance, CS, will have two possible values, C, E1, E2, touch, and C, E1, E2, no touch. Right. We don't know which one of these we're going to measure, right? But this will be a variable sensor capacitor. So now we're going to do, again, not full circuit, but just like get a feel for the circuit. I have this sensor CS, right? I don't know whether the finger is touching it or not. It's just some variable. We're going to mark it like this. It's a variable capacitor. So it's one of these two values. How do I design this first circuit? I want to add some charge to this capacitor while having a fixed voltage on that capacitor. Yeah. Okay, I can use a switch. And what else do I need? A voltage source, right? So a voltage source has a constant supply, has constant voltage. And I need a switch to define when I'm going to fully charge that capacitor, right? And that's what we did last lecture, right? So we will have, let's say, a voltage source, Vs, and then we're going to add a switch here, right? Let's call this switch S1. At some point in time, I will turn that switch on, and this capacitor will get some Q sense, which is what? If I close this switch, what is Q sense going to be? Vs times Cs. Okay, so that Q will be defined here. Okay, so once I have that, now I have to worry about the second phase. And the second phase is, okay, I got some charge. Because this is fixed, this charge is not proportional to whatever Cs is. If Cs is small, meaning no touch, Qs will be small. If Cs is big, meaning I touched the electrode, Qs will be bigger as well. Right? So I have that translation from capacitance to charge. Now I have to figure out how to turn this charge into voltage. Right? So to do that, as we did here, we had to add something. What was that? Another capacitor, right? C fixed, a known capacitor. Right? So the second phase, if you will, of this circuit will be that I detach it from the supply and then I add the capacitor. So let's see what happens there. I have this Cs. I had Qs here. And now I add another switch, and this is C fixed. Okay? So imagine that C fixed was empty, right? Before I turn on this switch. So CS got fully charged. I turn off this switch. Now CS is a bucket of charge that holds amount Qs. And then I turn on this switch. And now there's a full bucket of charge here, and there's an empty bucket of charge here. What happens? Yes? Correct. So, yes. So the answer is part of this charge will basically just flow to this plate over here. Right? It's just if you have two buckets, right? One is full of water, another one is not, and you connect them with a pipe, charge or water will flow until the levels even out. The level here is voltage, right? It's the effort by which keeps the electrons or the charge on the plates, right? And so remember, there's positive charge here, right? And if there's zero here, it wants to go there because it's repelled by its friends, right? So it just goes there, there's least effort there. It's much more comfy, right? It's a whole empty capacitor, right? So it's a very crowded thing here, and then, new space opens up. It's just like with housing or stuff, right? So charge likes that. But we can actually go and compute that, exactly how the charge will redistribute in a minute. But I just want to tell you basically that this is kind of step one, step two, and then from this new voltage, we will be able to figure out what exactly is this new change, right? So let's put the whole circuit together just so you see it before we break it apart again. So our full thing will be Vs, and then we have S1 here. This is CS. C fixed. S2. And I told you that C fixed was discharged, right? It was empty when we did that step. To make sure that that happens, I need to add one more switch here. So that switch will essentially, let's put it, doesn't matter. Let's put it on this side. That switch will be here, shorting the plates of this capacitor, right? So S3. Now, when I draw something like this, or you draw it, this is not a full specification of the circuit. You need to say which switch is on and what phase, right? Because that will tell us actually how the circuit works. Like this, you have no idea, right? And so we're going to say that in phase one, Okay? This, we'll call this phase sense. Okay? So in the sensing phase, S1 is on because we're actually charging the capacitor here. So S1 is on. S2 is off. And S3 is on. Okay. And in the phase 2, this is share or measure. So let's say measure. S1 will be off. S2 will be on. And S3 will be off. Okay. So this is kind of like given, right? You basically get, if you get a problem, you may sound something like this. Here's a circuit, here are the two phases. Yes?
Could you explain why S3 has to be on in phase 1?
So when S3 is on, as we'll do it, we're not going to go through each phase and just break it apart. But just in short, if S3 is on in phase 1, the plates of this capacitor are shorted, right, through this wire. So the voltage across it is 0. That prepares it basically for phase 2 when it needs to be shared, right? So that you know there's always 0 charge on that other capacitor. Even whatever happened before, this kind of like removes the history, right? Whatever was before, you don't care. Now you want to do the measurement. So it's a clean capacitor, right? It's empty. Okay. So whenever you get circuits like this, you essentially apply a recipe, right? And a recipe basically goes like this. So one is you basically draw a circuit for each phase. Right, so let's do phase 1. By the way, these two nodes are E1 and E2, right? People get that. Just so there's no, yes?
Sorry, why do you need S3 if S2 is really on? If S2 is on, isn't the circuit for C fixed really open?
Sorry, what's the question? Why do I need S3?
Yeah, if you really have S2 being on.
So if S2 is off, that's a good question. If S2 is off and this one is off, does the charge stay on the capacitor or not? Yeah, it has nowhere to go. So when the S2 is on again, then I would be sharing the charge from this bucket with this bucket, which is now half full, right? So imagine I have a bucket full of water that's at some level that I want to find out. And here I have an empty bucket. When I share them, I will know exactly what voltage I'm going to get. That voltage will represent that sensed charge, right, Q sense. But now, if there's some residual charge sitting here from like a previous cycle, then I no longer know what was the change here, because there's a little bit of error there, right? So that's why before every sharing cycle, we zero out that voltage. Right. Okay. So we have CS, we've shorted S1. This was S1, right? S2 is open. I mean, I can draw it just so people see it. So this is S2. C fixed. And there's S3. Okay. So we draw the equivalent circuit when the switches are in their own state. That's step one. Step two, we mark the voltages and charges on the capacitors just according to the convention, right? So mark Q's and V's on caps. So let's do that here. Okay, this one, there's a voltage. Okay, I'm gonna call this something else, V supply. This will be V sense. And sense charge will be here. Notice this is purely arbitrary, okay? I can go and flip this arrow and mark the bottom plate QS, it will be fine. It's just basically like marking the flows of current in the circuit. You mark them, if they come out negative, okay, fine, big deal. It was the other way around, right? So don't worry about that. When you're setting it up, just mark it somehow, but then be consistent from that point on, right? So don't change it somehow in the middle, right? So here we mark the top plate, QS, and then again, the voltage that's pointed to that plate is VS. And now for this one, we can go and write out that QS equals CS times VS. Right. Here, we can also, let's mark this voltage VF, right? And then here will be charge QF. Let's call this CF, it's shorter. Okay, so here we're gonna have QF equals CF times VF. Okay. What I also like to do is I like to add an index that tells me in which phase I am. Right, so this is phase one. So I'll add 1 here for the charge, because I know that's the charge on the capacitor in phase 1. Okay, so can anyone tell me what is VF? 0, right? This is 0, and so the charge is QF1 is basically 0. So let's label it QF1, CS1. Okay, what is QS1? Well, to determine that, we already have it. It's CS times VS, but what is VS? VS is equal to V supply, right? This is an ideal wire, this is an ideal wire. So basically VS is the potential between the potential difference between these two nodes. Those are the same nodes as the supply, right? So it's CS times V supply. Okay, so this is all we can find out from phase 1, right? Are there any questions for this circuit? Yes? If I have all the, oh yeah, so you're asking if S2 is now on. Yeah, so now that will be an ideal wire right here extending. So the potential between these 2 points would try to be 0, right? But then on this side, this source is trying to keep that at VS, so that would actually be a boom situation, right? Because you're shorting an ideal voltage source, right? So that's kind of an undefined condition, essentially, because it's trying to keep VS on its terminals, but you're shorting it, so you're forcing a 0 voltage across. Right? There was some other hand? Yes? Can you speak up? Yes, so whenever the problem happens, well, most of the time you're going to be given the phases if you're given a circuit to analyze. But if you're designing a circuit like we're doing it here, we kind of broke it into phase 1, phase 2, just by thinking how we're going to do the design, right? So usually, with these are called switch capacitor circuits, each phase does some part of the job, right? So then you just have to figure out how to arrange the switches, and sometimes you won't really get it from the first. So for example, you may design this circuit like without S3, and then realize, oh, gee, you know, when I'm charge sharing, there's this extra value there that sits, right? Because if I didn't have S3, I wouldn't be able to write this equation. I would be able to write something like this, but I don't know what QF1 was, right, previously. So that kind of complicates things. But normally, if it's just an analysis task, yes, you will be given the whole thing, and then just go and write it. Yes?
Why is VF equal to 0?
Okay. So the voltage, VF, is between this node, let's call it A, and node B, right? I can, if I trace this wire, it's an ideal wire connecting node A and B. Ideal wire has 0 voltage drop across it. That means that the potential A and potential B are exactly the same. And since this voltage is a difference of these two potentials, then it's 0. Right? Okay, any other questions? This is kind of like this circuit, I used to get a lot of questions like, okay, why doesn't the current flow here, right, through this wire, right? But keep in mind, the answer is you need a full circuit for current to flow. Current cannot flow through a single conductor because that would mean depleting charge from this part and then accumulating it here, but some force has to do that, right? So that doesn't work. You have to have, keep in mind that this supply voltage is a force that basically circulates stuff, right? So it needs to get charge and lift it up and push it across, right? So you need a full circuit for things. Just like water to flow, you need a full circuit. Okay. Phase 2. So in phase 2, I can draw the supply. I'll just draw the whole thing, but you know, usually you're just gonna draw stuff that matters. Supply doesn't matter anymore because S1 is open. So, okay, this is S2, right? So this is the phase 2 circuit, right? And again, what we're going to do is just like we did in phase 1, mark Q's and V's on caps and then calculate. Now, it is very important in this step for consistency purposes to keep the sign, right? So here I'll have plus, well, let's call it like plus QS2, and here plus QF2. This will still be voltage Vs. This will be voltage VF. If I'm writing on the same page, I would also label these voltages with index of the phase, just because this VF is not the same as that VF, right? So you can choose to do that if you want to. Maybe it's easier, so let's do that. VF1, VS1, VS1 here. So this will be VS2, VF2. So now we're going to just write them for this. So we have QS2 equals CS times VS2. And then we have QF2 equals CF times VF2. So there's one important piece of the puzzle between these two phases. And that is to watch out what happened with these plates as these switches change their state. Right? Notice that when I take the switch and I hook up this cap to the supply, right, the supply will just dump charge, or if the supply is lower voltage, will take the charge away from the capacitor. Right? But if I open this switch, the charge stays in the capacitor. So imagine I'm transitioning between this phase and that phase by first opening S1. So then I preserve whatever the charge is here. It's now a bucket full of charge. Right? And then I open S3. So now there's 0 here. And they're both like floating. They're just standing in the air. Right? And then I connect S2. So if I'm doing it in that order, this charge that was on CS doesn't have where to go except to this capacitor. Right? So then I can write the charge conservation for this node, right? This node over here, and I'll write it as QS1 plus Q, or maybe let's just do it in a better place. So we have charge conservation. So that's like step 3. Between phase 1 and phase 2. To see where the charge conservation happens, you have to see which node basically floats between phase 1 and phase 2. In this case, it was this node, E1, right? So when it got charged, I disconnected the supply, so the only place this charge could have gone is on this plate when I short them. There's no other supply or anything or ground or short connected essentially to that node to empty the charge somewhere else, right? So the charge is right there. And the charge, I can write it as QS1 plus QF1. So this is phase 1 equals QS2 plus QF2. So this is phase 1, one charge on E1, and this is phase 2. Okay, does this make sense? It's a pretty critical step. Right. And most of the stuff, when you're looking into the circuit, you'll be trying to find this node as you're flying, as the switches are changing, essentially, where's the node where the charge was conserved? Right. Right. Okay, if it makes sense, we're going to solve it. So we have CS VS1. QS1 is just CSV supply. Right, so that was our QS1. And then we have 0, right? That's QF1. And that equals, so let's take a look here. What are VS2 and VF2? In this circuit over here. This is a short, this is a short. VF2 is this voltage across this, and VS2 across these two nodes. So they're the same, right? And let's say that that's the voltage we actually want to measure in the circuit. So I'm going to say that VS2 equals VF2 equals V out, right? So that's what I want. So then this becomes CS times V out. This one over here becomes CF. Sorry, this is CS. Yeah, CF times V out. So then I write it here as CS times V out. That's QS2 plus CF times V out. That's QF2. And now you can group these two. So we get that CS times V supply equals CS plus CF times V out. And from there we can write out V out, which is what we want. V out is CS over CS plus CF times V supply. Okay? So this is our measurement voltage. Right. If CS is smaller, the voltage is smaller. If CS is larger, the voltage is larger. And by having a measurement circuit attached, or like a voltmeter, or we'll see actually very shortly some other type of circuit, we will be able to know what the voltage difference is, and we'll be able to calculate. So let's do like a numerical example. Just see what values I had there. Okay, so this is kind of a close to what you're going to see in the lab. And I'll let you calculate and tell me what it is. So, let's say that our CS equals 50 femtofarads in no touch condition, and 100 in a touch condition. And also CF is 100 femtofarads. Okay? And let's say supply voltage is 5 volts. So the question is, what is V out in the no touch condition and also in the touch condition? Okay, so why don't you take a minute and try to figure it out. Okay, any volunteers? What is the no touch value? 5? Okay. So let's just spell it out a little bit. Okay, so V out, no touch, will be equal, so CS with no touch is 50, right? Over 50 plus the fixed is 100, right? And then times 5 volts. So that's 5/3 of a volt. Okay, so what is with touch? Five halves, right? So it will be 100 over 100 plus 100 times 5. So it will be 5/2 volts. Okay. So this, the voltage difference between these two is what you need to sense to be able, or measure, detect, to be able to say, okay, I can now distinguish between a touch condition and a no touch condition. Okay? Now, if I'm only interested in whether the touch occurred or not, I don't care how close the finger was to the electrodes or anything like that. I just want to know, is the finger there or not? Okay? I just need some type of circuit that will distinguish between these two values. Right? And we'll do that circuit very shortly, and you'll use it in the lab a lot. The computers basically like a lot these types of circuit that will just tell them, hey, there's something there or not. Right? That's a single bit of information, 1 or a 0. Right? And these kinds of circuits are called comparators. I just want to compare these two values to some other reference value and know, okay, if it's below that, I get a no touch. If it's above that, I get a touch condition. Right? So if I was showing this kind of on a number axis, right? This was the V out, right? So this point here will be 5 over 2 volts. This point over here will be 5 over 3 volts. Right? Where do I put my decision threshold to be able to be most immune to any noise or anything like that that can kind of corrupt this measurement, right? Any uncertainty in the finger maybe exactly pushing on the screen and things like that. In the middle, right? Exactly. You find the point, which is basically 5 over 2 plus 5 over 3 over 2 volts, right? And you position your, so this is called a threshold. Right there. Or we're going to call it Vref. So the reference, there will be some reference voltage that we will use right in the middle to compare to these two voltages. And I'll show you shortly what that comparator circuit looks like. But before that, I kind of want to wrap up this whole 2D, how it actually looks, right? Because we've only done like one slice, 2 wires crossing. But as you've seen in the resistive one, there's a lot more wires on that screen. So let's figure out real quick how that works. Okay, before I go there, any questions about these 3 steps that we did? Writing the phase, writing the charge per phase, figuring out the charge sharing equation between the phases. Yes? Okay. So the question is, how do we know that this voltage is the same as this voltage? This is a great question, and this is exactly why we draw circuits in these phases. Right? One thing to note is that, okay, I missed to mention it, by the way. The key word is steady state. Okay? So when I draw a circuit like this, right, and now this switch S2 turns on, I'm going to turn it on, and I'm going to walk away and wait for everything to settle in that circuit. You remember last lecture we said if the switch is not ideal, there's a little time before the capacitor gets charged through that switch, right? And here we're using ideal switches, so you don't have to wait anything. But we basically say we look at the time when the capacitor voltage has actually settled to a steady state value, fixed value. That means the current here is 0. Right? There's no more current, there's no more flow of charge, everything's quiet. Right? Charge has redistributed. If you think about buckets of water, you added a pipe, the pipe drained the bucket, the levels are now equal. Now you come back and say, okay, what's the level, right? So in that situation, that's how we're looking at this circuit. Everything's settled. And then I'm just wondering, okay, this is node A and this is node B, right? Isn't this also node A? That's just a short wire, right? Isn't this just a node B? Right, so then VS2 is a voltage between node A and node B. VF2 is also a voltage between node A and node B, so they're the same. Okay, yes?
Is the circuit the same whether you touch or not?
Is this, yes, it's basically, the question is the circuit the same whether we touched or not, right? When we did the equivalent capacitor early on, we just saw that the value of that CS changes, but if there's no touch, there's still the basic capacitance between E1 and E2. If there is a touch, you just add more capacitance, right? But overall, that whole thing is just one equivalent capacitor, right? That changes value. Yes?
Can you put together the entire process, summarize using the delta T
Okay. I sort of erased that, but let me maybe walk you through this process again. So we start from a circuit. We draw a circuit for each phase. Right, so that's step one. You draw a circuit for each phase, again, in steady state. Okay, so that means, in this case, this switch is on. This capacitor has been fully charged to this supply. There's no more current flowing through it. Right? So for the steady state, you mark Q's and V's on the capacitors, like we did here, QS1, VS1. And then you write down QC, V equations. Right? You do that same thing for phase 2. And then you also go and write out, I hope I have it, the charge conservation. In this case, we did charge conservation on this plate and on this plate because they were, in this phase, they were separate, right? So they had some certain amount of charge. In that phase, we shorted them together, so that's now one node. So the charge couldn't go anywhere. It had to, basically, whatever charge was previously on this one and this one, when we shorted them together, it had to stay on either this one or this one. So that's why the sum of the charges in one phase is the same as the sum of the charges in the other phase. Right? Yes?
What's doing the switching?
What is?
What's doing the switching?
What's happening during the switching, you mean?
No. What is performing the switching?
Oh, what is doing the switching? Some controller, right? So in the lab, that's your Arduino little microcontroller. In the phone, it's also a processor. So some digital block does it. In fact, when we do the oscillators in a few weeks, this could basically just be actually an oscillator on its own that periodically turns on one and the other, right? So it's like a clock, right? And the refresh rate could be, let's say, a few tens of kilohertz. That's faster than your finger action, right? So, and that's enough. Yes?
How does this system go? How long does it before switching from phase 1 to phase 2?
So that would be this controller. Or if we do an oscillator, it's basically just some period, right? So let's say 1 millisecond in one phase, 1 millisecond in another, and then it comes back. Right? And a millisecond is much faster than I can move my finger, so that's enough to sense whether the finger is there or not. In fact, multiple times, and then average out these decisions and say, yeah, finger is absolutely there. Right? Yes? Okay, so the purpose is basically distinguishing between these two states. Right? In a no-touch state, we got 5/3 of a volt. In a touch state, we got 2.5 volts. Right? All I want to know was a finger there or not. I don't care whether this was 5/3 plus a little millivolt here and there, and also this. Because in life, there's noise and stuff like that in real systems. So you're going to be getting not exactly this point, but like some number of measurements around this, and also some number of measurements around this point. But all you care about is that your decision threshold is far away from that fuzz. Right? Because in the lab, when you're measuring a no-touch voltage or not, you're never going to get exactly the same value. If you manage to do that, please tell me. I'd love to buy that, whatever piece of equipment you have. So you will get some range of measurements for no-touch condition and for the touch condition. But all you want to know, was there a touch there or not? And you want to know it for certain because you want to drive your app or something, right? You want it to basically have almost 100% detection, right? So that's why you're going to make these two levels as far apart as possible and put some decision in the middle. And we're going to show what the decision circuit is in a moment. Any other questions? Okay, let me quickly just draw, we can do the comparator on Thursday too. I just want to complete the two phases, the 2D. Okay, so we had one stripe, and I'm just going to draw another one. I'm going to label this E1, 1, and then label this one E1N. And there's this stripe and the last one. And there's so it's basically, again, the whole screen is weaved, right? And so this electrode is E21, and this one is E2N. It could be N, it could be M, whatever, M, right? So it's an N by, or M by N type of screen. You can view each one of these points here as your little pixel, right? It's a pixel where the detection happens. That's your resolution. And there will be one wire right almost next to it, but not touching, right? All the way to the nth wire. So now what we need to do is, just like we did for this one and this one, we hooked up essentially the supplies and switches. We're going to do it for all of them. Right? So I have one supply voltage here. Okay. And I'm going to connect it to each one of these through a switch. So this is my switch 1. Right. Now, just for ease of it, I'm going to draw this sign. This is ground. So wherever I draw this sign ground, that means all these wires are connected to that node. Right? So don't be alarmed by that. It's just some zero potential node in the circuit. Okay? So I have E1 and E2. Okay, so now I'm also going to have, let's see, T1. I'm going to have a switch, or actually I don't need a switch here. It's fine. This is going to be grounded. Right, so look at the circuit. We're just doing this part, V supply and the first sensing capacitor. And we have S1. Right? And then I'm going to draw essentially a C fixed here for each column. Again, this sign means ground, means these are connected, basically, that's all. So this is CF1, this is CFN. We have a fixed capacitor or readout capacitor for each column. Okay? And now I have a switch here. That is my S2. So I'm going to say S21 through S2N. Okay? And then I'll have also a switch that discharges the, so S3, 1, S3N. Okay? So how does this thing look like when we're reading out? So we're going to read out Now, depending how many measurement circuits we have to read the voltage, we can either read all of these columns in parallel, or we can read one column at a time. It doesn't really matter. One thing that I want to show is I need a switch here, actually. So this switch is extra from what we did, and you'll see why it's needed. So let's call it S4. S4M. So let's say I do everything. In the first phase, I will basically connect all of these S4 switches to ground and short all S1. So S1 on, S4s on. And so that will charge all these pixel capacitors, all the sense capacitors. Right? So I have a circuit like plus minus Vs, and then all of these sense caps. CS11, CSMN. So they're all charged. And then what I do is basically I open all of the sense caps except the first one. So I have now this. These are just floating. And then I'm charge sharing with CF1. And this is CS11. These guys are CSJK. Notice because this bottom of the capacitor is not connected to anything, this capacitor holds its charge. So this charge sharing doesn't affect it. I still have the same situation as over there. CS11 charge shares with CF11. Meaning this pixel charge shares with this capacitor and no other pixel. And then I can interrogate each pixel at a time and get the whole thing out. Okay? Okay, thank you.